What's today? What's going on? What's wrong?
So you think programming over accounting?
Yes. If you're talking about career, it will be better for you, especially if you're going into engineering.
But in engineering we will be studying programming.
Yeah. But there's so many languages. So pick a language that you won't do at university and do that as well. So if at university they make you use Python, then learn Java. Because this will distinguish you from other candidates. You know? Okay, current carrying conductor in a magnetic field.
But I don't want to end up working on computers.
It's not about... Yes, but if you did your accountancy, you could have just said the same thing. I don't want to end up doing books. You're doing it to distinguish you from other candidates during the job application. Not to actually use it. You know? Yeah. What do you do in your free time? I like the jog. Okay, so we want you to be an engineering student here and also jog during the day. You know? Do you get my logic?
Yeah.
Why do you seem unhappy? Because I'm right.
No, because I prefer having something other than computers.
Fine, do accounting. I'm not your sponsor. I don't care what you do. You asked me for my opinion, and my opinion is you would be better off doing programming than accounting. That's my opinion.
Did you ever do accounting before?
Yeah, I studied business.
And did you like it?
It was fun.
Did you study accounting?
No, I studied general business.
No, that's different.
Yeah, I know. I know. That's why I'm looking about the ACCA exams.
Accounting is like the boringest thing ever.
Yeah, but I did statistics.
It's not.
Anyway.
You did accounting?
Yes.
Okay.
Yeah, Yusuf, please stop using facts to disprove Faisal. He doesn't like that. Okay. You got this written down? Please. You have this? Yeah. Okay. Continue. Oh my goodness, stop, would you please? You're distracting me. Continue. Alright. So, we learned when we have a current in a magnetic field, we get a force. It moves. Lee. I was just saying to the other teachers this morning how wonderful the engineers are to teach. Please don't ruin that. Okay, so we have a current in a magnetic field and it experiences a force, and we can find the direction of the force using the left-hand rule. This we did yesterday. Yep. Now, what is quite interesting is you might be thinking, well, what about if I change this a little bit? But just before we look at that, I just want to modify slightly the formula that we had. So, anyways, yesterday we had the formula F equals QVB. And I know the multiplication is a special multiplication. What did we call that special multiplication yesterday? Do you remember? Cross multiplication, yeah. Now, instead of having a single charge moving in the field, let's imagine we have a current in a wire. This formula does not have I in it, it has Q in it. But if you think back to electricity, does anyone remember the formula for I?
QV.
That's, yeah, another one was Q over T as well. Yeah? So Q equals IT. So you could change this into ITVB. But let's imagine you also knew the length of the wire. Well, if you think about it, length is like distance, and we have speed and time. What does time equal? Distance over speed. So this time here, you could replace it with... Did I got that right?
Yes, and you cancel the speed.
Yeah, I have I L over V B. And the V, oh sorry, and the V cancels that. So you're left with Bill. So this is the formula for the force when you have a current in a wire of length L inside a magnetic field. So just like in my picture here, when you have a wire with a current of length L inside a magnetic field, you get a force. So what you notice is if you make the wire longer, you get more force. Or if you increase the current, there's more force on the wire. So this is a new formula, although it's really just kind of the same as what we were doing yesterday.
Does this also require cross multiplication?
No, actually, because
Cancelling.
yeah, because this is a scalar, this is a scalar, and this is a vector, and this will be a vector. Actually, no, good question, does it? Yeah, actually, you're right. The I is kind of like a vector because it needs to have the direction as well. So yeah, you could use the same. Yes, to answer your question, use the left hand cross multiplication here to get the direction. Yeah. Okay. Did you write this rule down? Yeah. Continue. Yeah. Okay, continue. So we have our F equals Bill formula. And in this formula the current is perpendicular to field. If it was not perpendicular, that is if it was an angle theta, then let's see what the formula is. So let's instead this time do something we haven't done yet. Previously the charge and the current, they were perpendicular to the field, but let's put them at an angle to the field. So for example, let me draw it like this. What?
I don't know what this.
Do you have the answer? No.
We have to resolve.
Yes.
Yeah.
So be quiet. Right. So in the past, it was like this. But now what we'll do is we'll put the current going at an angle. Yeah. So I think we'll measure the angle, we'll call it, yeah, theta. So we'll put the angle here as theta. So what we need to do is we need to resolve this into this direction and this direction. And let's call the current here I. Well, this one here will be I cos theta, and this one here will be I sine theta. And this one here, we don't care about it, because if you think about our left-hand rule, we need the current and the field to be perpendicular to each other before we can get a force. If they're in the same direction, it doesn't work. So we only actually care about this component. So the only thing that's changed is the I has become I cos theta in the formula. And that's all. Now the reason I have sine theta here is because I didn't make it clear in my text, but actually I think it's more normal to measure the angle in this direction. So I'll just change that for you.
Between the angle between the current and the
oh yeah, of course it is. Sorry, I said the angle theta between the field. Yeah, so I should have been measuring from the field. Sorry about that. So that should have been sine theta there. Anyways, you don't have to worry about this in the exam because this formula is in the formula book, and when they give you the angle, it will be in the direction, so you can use this formula. That is in the direction of the field. So you don't have to worry about resolving it in the exam. They'll give you an angle and they give you this formula in the formula book, so you don't have to worry about if it's sine or cos. Okay? So this is if we're at an angle theta to the field. Can you write that down?
Right, what's that?
This new formula. The only difference, Andrew, is the sine theta. It's okay, Lee? So what happens if the angle is 0?
There is no force.
Yeah, because then the current and the field are together. If the angle is 90, then what formula do we get?
No, sorry. BIS.
We get Bill, maximum. What about if it was an angle of 45?
Half Bill.
No.
Bill times 2.
No.
I give up.
Thank you, Lee. 1 over root 2. Bill. Because sine 45 is 1 over root 2. Or 2 over root 2 over 2. Same thing. Okay, continue. Now, if a force acts on a current in a magnetic field, then could we use this force to do work? Yes. Yes, we can. And this gives us what we call the DC motor. Yeah?
Yes.
You've seen this before? Now, this is pretty nice because what's happening here, if you look in this direction, which way is the current? Into the page, so that's this way. And which way is the field? Yeah, the way my hand actually is to the window, isn't it? So which way is the force? Up. So you can see here in the picture there's a force going up here. Now if we go over to this side, which way is the current? From my point of view, the current is to me. So for you, it's to you. And then for me, yeah, so the force is going down here. Now if you connect these two wires in a rectangular shape, if this force is going up and this force is going down, what will happen to this shape? Yeah, it'll want to turn. And this is how you can make a DC electric motor. So a DC electric motor is actually quite simple. It's just a square-shaped conductor inside a magnetic field. Now there's a little bit more to it than that, because please note that these two ends do not touch. This gap is very important. Anyone know why? No? If this gap wasn't here, the current would simply go around through here. You're trying to force the current to go through the field, so you put a gap here. So to complete the circuit, the current must go around this way. Now, does anyone know what these brushes are for? Like, why don't we just connect the wire directly to this haft here?
Every 90 degrees.
Yeah, but
All the energy.
oh no, way off base, way off base. Why don't they just connect the wire with a little pin or something onto this? Why got the wire connected to a brush and the brush is brushing this wheel? Why don't I just simply attach it? Why do I do this business with the brush?
This friction.
No, actually this makes more friction because the brush is rubbing against the wheel.
Is the
That is
commutator
electricity.
turning?
Say again?
Is the commutator turning? Like
Yeah, this whole yellow structure is turning.
So that it can turn. So like if it's connected directly to a wire, then the wire will have to turn with it.
Exactly. If this wire was pinned onto it, then the wire would very quickly twist up, which of course you don't want. So by having the current go through a brush against the wheel, you can still have the current travel through the wheel, but the wire doesn't have to move. So these are called commuter segments or commuter rings. And they're usually made of conductor like carbon, and they brush against it. So of course, because of the friction, it means every so often they will need to be replaced. Now I think what usually happens is the commuter is quite thick, so as it wears down you can just like slide it in more, and then once the carbon is worn away you just put a new brush in. Yeah. So you can see it's a very simple design. Before I get you to draw it, let's calculate the turning force. So, does anyone remember? I sure hope so. What is the formula for turning force? For a couple.
My strike.
Because this is a couple. Remember couples?
Remember couple, don't remember the formula.
Force times distance.
Yeah, what distance though?
Perpendicular distance.
Oh no.
Distance between the two thingies.
The diameter.
Yeah, the two radius.
So the total turning force of this coupled system is the force here times the diameter. But we have a formula for force. It's Bill.
Bill D.
And then we have the D here from that. Now if you look at this, L times D. So this length times this distance makes what? Area, very good. So this is VIA. Now if you want to make the motor more powerful, what you could do is actually wrap the wire around many times, then each wire gets a force. So if you wrap the wire around n times, what do you think happens here to the formula? Times n. So the total turning force of the DC motor, the torque, or turning force, is, the student pointed out you can spell the word IBAN, which, because it's a bank now, easy to remember. So the torque is, the DC motor is IBAN. So you want to make the DC motor more powerful, you can either increase the current, increase the magnetic field density, increase the area, but that's kind of difficult, increase the number of turns of the wire. Okay, so write down this formula and you will need that diagram for the exam, so you'll need to draw this. You got this formula, Andrew? Yeah? Okay. Do your very best to draw the DC motor.
That's a different name.
What is torque? It's a synonym for turning force.
Could you put that in words? How would I write it? The
Right.
number of what?
The N,
Yeah.
a number of loops of the wire,
Oh.
number of turns of the wire. So like in my picture,
The armature?
the armature is just the name of this turning system. I don't use this word armature, but it's the name of this rectangle. N is how many times the wire loops around the armature. In the picture, you can't really tell because the wire might be inside this armature structure. So as far as you know, this copper wire could maybe loop around it 10 times before it comes out.
One second, you're talking about, so this is like a casing.
It could be just a case. Yeah, it's really just a casing in the picture, because otherwise, your wires would be falling out or something. So, like, I'm imagining this armature as being some casing for the conductor.
Will you be asked to draw it on?
Yeah, it could be. What's
How does the looping it change anything?
Yeah, like how does having the copper wire go around like 10 times? Because that formula, Bill, it's the force per copper wire, per conductor. So if the wire is insulated and looped around 10 times, it's the equivalent of having 10 forces on 10 wires. Now the key thing, that's actually a key thing, it's important that the wires are insulated so that you have the effect of having multiple wires. If the wires weren't insulated, then it's just like one wire then. Okay, can you draw this in your notebook, please?
What's the blue line? What's the line? What's the blue?
Yes, it is.
We're meant to label it too.
Yes. Did you draw that?
I used to collect bus motors.
Got any here? Got any here?
When I was like 11, 10, there was a cartoon about cars. So I used to collect them and then find out which one is the fastest and then put it in my car and race.
Happy times. Transformers, was it?
No. I don't think you'd know it.
You might be surprised. What's it called?
Yeah. I'll get the name.
What's the English name? You know this?
Faster and follower.
What?
The translation. Faster and follower.
Faster and follow?
Let's go. Let's go. Let's go. That's the name of the anime. Bufuso Kyodai. Let's go. Let's and go. Let's and go.
Let's and go?
Yeah.
What type of grammar is that?
Japanese translation.
Wow, yeah, you're right. I don't know it. Two boys, Retsu and Go, begin their dreams to become mini racers. Sounds right? Nice. Maybe as a class project we can make an electric car. It's true, yeah. Oh, there's been video games.
Yeah, I had the game.
And a film!
It's like 4 parts anime. This is the DC Motor. I used to collect them. They changed them. And then we used to stick the cars together side by side or one up behind the other to make them go faster and race in teams.
And would you put like little snails inside the car? You can do it! You can do it! Hang on.
And change the wheels.
Hang on. You can do it, Retsu! Go, Retsu!
When
Magnum.
when you're drawing like the symbol of the sun, how do you, which one is the positive and which
The long one is the positive.
longer is
You look confused, Andrew. What's wrong?
What does the blue arrow represent?
The field. North to south.
But isn't the force up?
True. Force is up. That's in red.
And the current is,
Into the page on the left.
so isn't the field supposed to be the other way?
No, that's the current.
No, your hand's right. Yeah.
What is the current? Yes.
Yes.
Okay. Wait, I'm confused.
The current is
Because so why is the current going that way?
it's so you look at
Because it's coming from the positive.
No, up there.
Here?
Yeah, that.
Yeah, because the current comes out of the positive side.
So it's going that way.
Dun, 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 dun.
So the current is that way.
Yes. But the field is going that way. Sorry, from your point of view, the field's going that way. Yeah. Yeah. It's okay. Continue. Or do we have to finish there? Well, I think we have IBAN. Okay. Yeah, we'll continue with this. We'll continue from this point then in the next class. That's the Greek letter for torque, turning force. I forgot what I used in mechanics. Did I use an L or a J? No, I definitely did not use a T for turning force. Definitely did not.
Yeah, no, you use the
tau.
Yes.
Tau.
Tau.
Do we have maths today?
Yeah, 3 to 5. Try not to die, please. Okay. We'll wrap it up there. It's a 1 hour class now.
A thought crossed my mind yesterday.
What?
So if the submission of the English and the math were on the same day,
Yeah?
And you said that we postponed it one day forward, and we didn't have math yesterday, so the submission was today. So, does that mean that the submission is tomorrow, next week?
What are you
No,
talking
it's
about?
something just right.
Yeah. When did you submit the English?
We're going to submit it on Tuesday next week.
You got an extension on the English?
No,
No.
already Tuesday.
Tuesday next week, yeah.
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 And
So,
this is,
Wednesday. It's a 3 o'clock class.
Later, yeah.
Tight schedule.
No, it is not tight schedule because you knew about this weeks ago. Weeks ago.
We had the physics coursework to finish. You know how long the physics coursework is?
We're making Tuesday.
Of course we are.
Yes, I know this. I've been teaching there for over 10 years. I know BS when I see it.
Yeah, of course. And you still decide to make all those submissions together.
What are you talking about?
If it was like we do the English, we finish, then we get the math, then we finish, then we get the physics, then we finish, it would have been way better for you and for us.
No, you see, you're talking a load of nonsense. Because number one, it's impossible to do this because there are more coursework than there are submission weeks. Because not only do you need the submission to be on its own week, you also need to be a certain distance into the semester so you have enough material covered.
Not for English,
Not for
nor chemistry either. They're not related to the subjects we're studying whatsoever.
I really don't. What I could have done, Faisal, is I could have moved the math and physics date before the submission of the English and give you less time. Then you would have one every week. Or I could have given you more time and trusted that you could manage your own study time like an adult. Oh wait, I think that's where it went wrong.
Hater.